Anthropic's AI model is called Claude. Now that's a real name. Why is it called Claude? Other AI models don't really seem to have first names. ChatGPT isn't really a name, is it? But Claude is. So why is it called Claude? Well, it turns out it's because it's named after somebody called Claude. And so in this video, we're going to ask, who is that Claude and why were they so important that they get a frontier AI model named after them? Well, if you want to find out more, please let me explain. So there are lots of famous people named Claude. Claude Debussy, for example, the influential French composer. Claude Monet, the famous painter. Claude Rains, of course, the famous actor. Is Claude the AI model named after any of them? No, no, he's not. Though that could be interesting, but he's not. It's actually named after Claude Shannon. They say he's the father of the information age. He's the guy that understood bits. So he was born in 1916 in Michigan. He died in 2001 at the good old age of 84. He did his graduate degree in electrical engineering and maths in 1936 in Michigan, and then moved over to MIT to continue his studies. Now, Shannon was fascinated by the work of the 19th century English philosopher George Boole. In his great work, Laws of Thought, Boole had formalized logical expressions which we know today even as Boolean algebra. That's where we get the name from. Then in 1940, he published his master's thesis, which he'd written a couple of years earlier, a symbolic analysis of relay and switching circuits, in which he showed how Boole's logical symbols could be treated as a series of on or off switches, which we know today, ones and zeros, binary, and how binary arithmetic could be carried out by electrical circuits. And this is absolutely fundamental. This became the springboard from analog computing to digital computing. So someone who could design a circuit to get two numbers added together just using binary, this was revolutionary. Of course, today it's we use it in every single computer we've got, every single smartphone, every single microcontroller's got this logic in it, but someone had to invent it, and that's who Shannon was. So here is the front page of that thesis, written in 1936, published in 1940. So why is it important? Well, first of all, it talks about switches and kind of an on and off state. Now, he expressed it in terms of the hindrance. So if something was fully hindered, which we would call off, it had a value of 1. So in kind of our today's thinking, it's the other way around. We kind of have the conductivity logic. It's on gives 1 and 0 gives off, but he was talking about the hindrance. So the symbol 0 will be used to represent the hindrance of a closed circuit. So it's 0 when there's current flowing through it, and the symbol 1 to represent the hindrance of an open circuit. That's when the circuit AB is open, it's got a value of 1, and when it's closed, it's got a value of 0. So it's the other way around because he's talking about hindrance, not of conductivity. However, he does mention in the paper that you could express it in either way. Today, we're more used to expressing it the other way around, but fundamentally, what he defined here was the same thing, just looking at it from hindrance rather than from conductivity. And so then in that paper, he went on to design an electric adder of binary numbers. So the idea was it would have some switches that you would set in binary, up and down, on, off, and then another set of switches, the other number you wanted to add to it. It would go through the circuit, and then there would be a result, which would be a relay, which would be on or off. Of course, it's a relay, you could connect that to a light or something, and it would then show the binary representation of the number that you're trying to add. And this is a direct quote from the paper. The circuit will automatically add two numbers using only relays and switches. Relays and switches, that's all. The sum will be represented by the positions of a set of relays. A number which is carried will be represented by relays. So there was even a carry bit. So any of you that have done any kind of assembly language programming, you know that this idea of adding two things, there being a carry bit, is fundamental. We use it all the time. I mean, literally, as I said, every single CPU of any kind has got an adding circuit in it, and this was invented by Claude Shannon, and he showed how to do it, how to go away from the analog world to a binary world, and how you can start to do maths on a binary set of numbers. And then having defined basically, binary computing, which was just fundamental, he didn't just sit on his laurels. He then came up with another paper in 1948, a mathematical theory of communication. And this was a landmark publication. his second revolutionary paper, and it is one of the most influential and cited scientific papers of all time, and it gave rise to what today we call information theory. It's actually been called the Magna Carta of the information age. So it was, again, absolutely fundamental in how we think about it. And today we live in the information age and the AI age. None of these things would be possible without Shannon's paper. And then before the digital age, none of it would have been possible without Shannon's paper. So what is in the paper? Well, first of all, he's the first time to write the word bit in a paper, a term that he says was suggested to him by his colleague J.W. Tukey, but he was the first person to actually write it down in a paper. He defined what is a communication system. Today we're just so used to communication systems, but at some point it had to be defined. And so he defined, you talk about the source, the information you want to send, the transmitter, the channel that it goes over, the receiver, and so on. So that's all defined by him. And he was the first person to talk about bits per second. So today we talk about, megabits per second or kilobits per second, or occasionally bits per second, depending on what you're looking at. And that was a phrase that was written in this 1948 paper, and we use it all the time today when we're talking about communication. But again, someone had to be the first person to get this stuff down and understand what it meant. So why does it matter? Well, it really was a paradigm shift in communication science. Before that, people thought about radio waves and telephones and signals, and that was kind of the analog world. And then when you get into this kind of digital world, you're talking about information, noise, probability, capacity, bits, error correcting, compression. These are all things that he touches on in this paper, and again, something that all of these things we use today. And here's a great quote: "The fundamental problem of communication is that of reproducing at one point, either exactly or approximately, a message selected, basically sent from another point." And that he wrote that as like in the first couple of paragraphs of the paper. And that's so obvious maybe to us today, but it wasn't obvious to people back then in the analog age. So absolutely amazing. And so there you go, Claude Shannon, a real giant at the beginning of the information age. Well, that's it. I'll see you in the next one.